Hello and welcome to Pep Talk with me, Mr. Pepperell. In this episode I'm thinking about states of matter and why solids, liquids and gases have different properties. By the end of this episode I hope you'll understand how solids, liquids and gases are different, how the particles in solids, liquids and gases are arranged, and why it is that a gas is much less dense than a solid or a liquid.
So this should be stuff you're probably pretty familiar with, to be honest, but let's recap anyway. Pretty much everything you encounter around you is either a solid, a liquid or a gas. And depending on its properties, we can assign all materials we encounter into one of these, what we call three states of matter. Okay, so if we have a little look here, I've got a picture of an iceberg, and this picture features water in all three of its states of matter. Okay, firstly I've got the solid ice there. Okay, I've got liquid water in the sea, and the clouds that we can see in the picture are water vapour or a gas. So in that picture we've got all three states of matter, solid, liquid and gas. So again, using ice or water or steam as our reference material again, let's think about these different properties and how they're different in the different states of matter. And the first thing I want to think about, can the material flow? Okay, now in the case of the solid ice, while it's a solid, no, that can't flow. But we should all know that yes, the water or liquid can flow, and also gases can flow as well. So we've got a difference there, okay? Solids, no to flowing, and liquids and gases, yes, will both flow. Okay, the second property, what about the shape of the material? Well, in the case of the solid, i.e. the ice cube here, that's a fixed shape. The ice cube is that shape. Even if you smash it apart, all the little bits will still jigsaw back to make that shape there. Okay, and it's a fixed shape. It stays in that shape while it's a solid. Okay, if we melt the ice, we get the water, which will then fit the shape of whatever container it's in. If you pour it into a cup, it takes the shape of the cup. If you pour it into an ice cube tray, it will go into the shape of an ice cube tray. Okay, and then if we go to the gas, well, the gas will fill whatever container you put it in. If you put it inside a little sealed box, it will fill the sealed box. If you open the top of the box and let it out into the room, this gas will then expand to fill the whole room. So we've got differences there in shape as well. Okay, next, what about the material's volume? Well, in the case of the solid, our ice cube there, it's a fixed volume. That amount of ice cube always takes up that volume, and it's the same case for the liquid as well. If you have a glass of water, you can't change the volume of that water. Water's practically incompressible, okay, so it will always be the same sort of volume. But like I said previously, a gas, the volume can be changed. It will expand and fill up the area that it's in, so you can change the volume. So for a solid, we've got a fixed volume, liquid, a fixed volume, gas, the volume can change, okay? And the last thing I want to think about is the density of the material, okay? By which I mean how much mass is there per unit of volume of the material, okay? So if we think about density of a solid, okay, a solid tends to have a much higher density, it's a lot heavier for the unit of volume, okay, than a gas is. If we think about a liquid, again, it's much denser, it's got a much higher density than the gas. And finally, if we think about a gas there, it's got a low density compared to a solid or a liquid. So we can see that these properties, ability to flow, the shape, the volume and the density, all vary for our different states of matter. So we know that materials can exist in one of three states, but they can also change between these states. And these changes are brought about by a change in temperature. So from this diagram, okay, we can see that we've got a solid, a liquid and a gas here. And on my diagram, my red arrows indicate an increase in temperature or heating. My blue arrows indicate a decrease in temperature and cooling. So we can see, for example, that if we take a solid, if we heat it up, i.e. we cause melting of the solid, our solid will change to a liquid. If we continue to heat it, more heat being put in there, okay, we can either boil or we can vaporize that liquid to make a gas. Okay, it also goes the other way. You've experienced this in the real world. If you take liquid and you cool it down there, you're going to solidify or you're going to freeze that liquid and it's going to become a solid. Okay, so have a little look at that diagram there. Just make sure you're familiar with the ways that these different states of matter can change between one and the other. This is the bit you might not be quite so familiar with. In a very rare occasions, you can heat up a solid and it doesn't melt first, it goes straight to being a gas. That's something referred to as sublimation. Okay, and we know about gas, i.e. steam, for example, might condense on your mirror in your bathroom to form a liquid, but some gases can also condense directly if you cool them down to form a solid. So perhaps just pause this, have a little look, and make sure you're familiar with the terminology of how one state of matter can be changed to another. So why do these changes actually happen? Well, it's all down to the particles the material was made of and something called the kinetic theory of matter. Okay, the kinetic theory of matter, as it says here, okay, it describes how the properties of material are related to the arrangement of its particles. Particles are the important thing here, okay? All materials are made up of particles, which are arranged in different ways depending on the state of matter. So let's have a look at some of these different arrangements here. Okay, first of all, here's some particles, and this is what I would expect the particles in a solid material to look like. So S for solid there, okay? The particles here are held next to each other in fixed positions, and they are vibrating ever so slightly, okay? These particles would be moving about ever so slightly. They are vibrating. The particles of any solid, even though you can't see them, are vibrating a little bit, but they're vibrating about their fixed positions. They don't move around each other, they don't swap positions. They vibrate where they are ever so slightly, okay? So that's what we'd expect to see with particles in a solid. But if we look at particles in a liquid, you can see they're arranged slightly differently, okay? Here in a liquid, okay, the particles are still close together, they're still in contact with each other, but they're moving randomly about each other. They're vibrating and they can move and they can swap positions, okay? So this particle here could swap with that one there, and they can move and move around each other. So they're different from a solid. It's the fact that these are randomly arranged and they're moving about in a random way. And that's what enables a liquid to flow, for example, or fill the container that you put it in. It's because the particles can move about randomly. They're not held in their fixed positions. And finally, if we look at the particles in a gas here, we can see that these particles are much further apart, okay? The particles in a gas are moving much faster, okay? They're randomly moving about, they're vibrating, they're much further apart, and that is what gives gas a much lower density than the liquid and the solid. We mentioned that before, that's one of its properties. So why did changing the temperature of a material change its state of matter? Well, if I increase the temperature of a substance, what I'm actually doing is giving it energy. And if I give energy to the particles in my solid that we know are vibrating slightly, if I give them more energy, that energy is converted into kinetic or movement energy of the particles, and this means they start to vibrate more. So if the particles in our solid here start to vibrate enough, they can start to vibrate out of their fixed position. So by giving them kinetic energy, they vibrate more. Eventually they can vibrate out of their fixed positions and our solid can become a liquid. Okay, my particles are still quite close together, but because they've got more energy, they're vibrating more and they've managed to get out of their fixed positions they were in. If I start to give more kinetic energy to my liquid, okay, the particles are going to start to move even more. They're going to start to move even faster. They're going to start to get a lot more distance between them, and eventually, when they've got enough distance between them and they're moving fast enough, our liquid can change into a gas here. So we can see that by giving material more energy, we can change its state of matter from a solid to a liquid and a liquid to a gas. And obviously it should be obvious then, if you take energy away from a gas, it can change back to a liquid. Take energy away from a liquid, we get back to a solid. Okay, now finally we can see that the particles up here in this gas are a lot more spaced out, okay, and this is what makes my gas a lot less dense than my liquid or my solid. So we can see here that as you increase the amount of energy you give to a material, its density decreases, okay. These particles are a lot more spaced out, which means there's a lot less mass per unit of volume that we mentioned earlier, which means that our gas is the least dense of them all, and liquid and solid are much more dense than the gases.
So that's it for this episode on states of matter and kinetic theory. Any problems on that, don't hesitate to tweet me at Mr_Pepperell or email me and I'll get back to you ASAP. Thanks for stopping by.